Hello, people of Earth. Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. So today we are going to talk about, answer to a very interesting question. What was our son like when he was young? And for this, we invited Meng Jin. Hi, man, how are you?
Oh, I just unmute myself. Hi, Frank. How are you?
Good, good. Meng Jin is a heliophysicist at the SETI Institute and at Lockheed Martin, and is the co-author of a paper entitled 1 Year in the Life of Young Suns, Data Constrained Corona Wind Model of Kappa 1 Ceti, which was published in August this year in the Astrophysical Journal. So we are going to basically talk about your research today. But before this, I just remind our viewers that we, first of all, tell us where you are watching us from, and you will be able to ask questions directly to us in a few minutes after Men explained to us basically the science and some of the results of his paper. So before we start, Meng, you one of these weird species of scientists that we have at the SETI Institute. There is very few of you, called heliophysicist. So what is an heliophysicist? What do you do every day?
So I think heliophysics basically focus on the sun-solar system connections. More specifically, is to understand the fundamental physical processes on the sun and its impacts on Earth and other planets in our solar system. Also, as well as the changing conditions in space between these solar system objects. And nowadays, as the fast advancing exoplanet detections, I think we can also define heliophysics from another point of view, that it is the integrating science that could help us determine the habitability of the exoplanet, because all the exoplanets are embedded in the stellar ring from their central stars. Yeah, so that's the heliophysics. Yeah.
Okay, thank you for clarifying this. So it's a very important part of the study of the universe, because stars are the main mass in planetary system, and stars interact with planets. And that's the reason we have heliophysicists at the SETI Institute, because people like you can tell us more about how a star behave, and of course, what will be the impact on the planet. So let's talk about this interesting paper. So I heard you have prepared a few slides to explain to us, to illustrate a bit, summarize this paper. So go ahead.
Okay. So I want to first talk about why Carbonaceti is important. So Carbonaceti is a star about 30 light years from us in the equatorial constellation of Cetus. So the one uniqueness of this star is that it has almost identical properties as our own sun. So they have the same spectral type of G5, and they have the same surface temperature of 6,000 Kelvin, and also they have a similar mass. So only exception is that this star is rotate 3 times faster than the sun, which is 9 days for the rotational period, which means this star actually reflects our sun in its younger age. So remember that during the star evolution, the star rotates faster at the early age than the later age. And during from the early age to the later age, because of the loss of angular momentum due to the stellar ring, the star will rotate slower and slower. So that's the reason the scientists can relate the rotational period to the star age. So the Kappa 1 Ceti is estimated to be only 650 million years old. So if you're assuming our sun is a human being in her middle age, like 40s, then Kappa 1 Ceti is only about 5 years old. So that Kappa 1 Ceti is like the infant of our sun.
So that's a toddler of our sun that we have access to. We can observe it, we can understand the way, maybe the solar wind, the kind of activity. Okay.
Yeah. So Kappa 1 Ceti provide us a window to look back in time for our own solar system. and especially at the time when life starts to emerge on Earth. So the information from this star will provide very important reference to explain the origin of life on Earth. However, due to the distance, we have a very limited information about this star. And for example, it's stellar ring. So because you cannot directly observe it. So, but this is important because it's known to have a very important role in shaping the planetary atmosphere and therefore the habitability. So on the other hand, because of we investigate our sun for more than 2 decades in detail, that we have tens of observations in high temporal and spatial resolution. And based on this data, we have built a high fidelity first principles based solar corona and solar ring models. So in this study, we actually tried to adapt a state-of-the-art solar model to reconstruct the corona and solar ring of stellar ring of Carbonaceti. So let me share several more slides about. So I want to.
So in the meantime, while you're preparing this, I want to say hello to some of our viewers from New Zealand, from La Porte, Indiana, from Worcester, UK, for Denmark, Saskatoon, Canada, London, Colorado, Germany, Delhi in India, Melbourne in Australia. Almost every continent is represented today. That's great. So welcome. We are talking about Kappa 1 Ceti, toddler of the sun, and why this is interesting and important to understand the formation and study the evolution of life. So, Meng, I love this name, the Alfvén Wave Solar Model. Maybe you can tell us what is exactly it is before.
Yeah, so this is the solar model I just mentioned. That so this model called Alfvén Wave Solar Model. So it's developed at the University of Michigan under space weather modeling framework. So so this is just to show you basic idea that how this model works. So the left part you can see we have the solar magnetic field observations for our own sun. So this is the line of sight magnetic field observed by a satellite called Solar Dynamical Observatory. So there's a HMI instrument on it to observe the magnetic field on the sun. And the black and white patterns you see are the magnetic field of the sun. And with the positive and the negative polarities. So this model, the awesome model, use this magnetic field to drive the model and to specify the inner boundary conditions. So, and then this model solve magnetohydrodynamics equations. So it's similar as a simulated fluid, but just with the presence of the magnetic field. So, and with that, we can actually build a sun in the computer. So, and here you can see the first row is the observations taken by SDO AIA, another satellite observing the EUV band of the sun. And also there are other, so this too is from the stereo, another satellite observing the sun from the other angle. So we can see the EUV emissions by the observation. And then the second row is the model synthesized EUV emissions. So you can see basically the model can reproduce the sun in EUV band. And not only that, so the right part is the in situ measurement we do near the Earth. So we can not only compare the remote sensing, we can compare the in situ data with the model. So
when you say in situ data here, we are talking about measuring the solar wind properties?
Yes, exactly. So that you can see the solar wind velocity, plasma density, temperature, and the magnetic field. So, sorry. Oh. So, and then here you can see we reproduce the sun in the model. Yeah. So this is a model we are trying to use for understanding the stellar wind from Kappa-1 So, but when you move to the stellar modeling, the one difficulty is that we don't have the privilege to seeing the spatial reserved magnetic field. So how you specify to drive the model. So instead of having a spatial resolution, we actually use the German Doppler imaging technique that is assemble the time series of a spectral line profile and try to reproduce the 2D distribution of the magnetic field on the star. So this is an example showing you how that could work. That here you can see, assuming a magnetic field, pure radial magnetic field in a sunspot. And here you can see the spectral profile you see over the sunspot is rotating across disk is changing. Mm-hmm. And also if you assuming the perpendicular field, I mean, in the perpendicular direction of the field, you can see the line is changing differently. So yes, with this technique, actually, you can reproduce the 2D distribution of the magnetic field. It's very similar as the MRI used in the medical field to reconstruct the picture of your body in 3D. Yeah. Anyway, so in this study, we used the observations from two periods, one in 2012, one in 2013, and you can see the reconstructed magnetic field is very different, and we use this to drive the model. And another difficulty is the corona heating. So we know that even for now, for the sun, the corona heating problem is still on debate. And there are several mechanisms can explain the corona heating, why the corona is so hot. So, but one dominant theory is the wave heating or the Alfvén wave heating. So basically, it's the corona can be heated by the turbulence of the waves. So with the solar model, we have observations to derive this corona heating parameters using the spectral line observations. And for stellar, we have the same technique that you observing the line. The line has a profile, and normally there are several components for the width of the line. So one is the thermal broadening, and like it depends on the plasma temperature. Mm-hmm. And also there's the instrument broadening. After you remove all this, there's still broadening. We call it non-thermal broadening. So this non-thermal broadening is related to the wave turbulence heating. So by observing the spectral lines by the Hubble telescope on the Kappa-1 we actually can derive this very important corona heating parameters and to use to drive the model. So yeah, so with that, we can reconstruct the 3D structure of the Kappa-1 that in 2 periods. So one surprising thing we see is that it's just separated by 1 year, the observation, but you can see how different the magnetic configuration is. So for 2012 period, you can see it's a very like a dipole field, but 1 year later, it's changing dramatically as a tilted dipole and also include a more like a quadrupole component in this configuration. So that means this star has a much shorter cycle period. Like we know the solar cycle is 11 years old or 22 years old, but this star is is very different compared to the sun. That so it also means the dynamo is very active, more active than the sun. So
which is what you were expecting for a toddler anyway, to have a more activity and to behave a bit yeah, like that, right?
Yeah. So imagine you the Earth in that system is experiencing the changes that much faster, much more dynamic than the sun in our than the Earth in our current solar system. And this is also we reconstruct the stellar wind. This is just like a 2D plot at the equatorial plane, and we overlay the Mercury, Venus, and the Earth locations, assuming they are there. So and see how different the Earth is experiencing in that when the sun is young. So this is the dynamic pressure, which is density times velocity square. So it's important parameter for the star planet interaction. So and this is we use the current Earth dynamic pressure as a scale that you can see how many times this stellar wind is stronger and how different the Earth is experiencing when the sun is young. So that is about, yeah. So, and also you see these structures, the arms here is called co-rotating interaction region. So that is caused when the slow stellar wind and the fastest stellar wind collide. And so it's enhanced the density and create these spirals. And the difference is that because, yeah,
so ahead. From this figure, we can say that if we had a Earth right now in orbit around Kappa 1 Ceti, it will basically have 100 times more solar wind of particles coming from the sun.
Yeah, exactly.
And sometimes crossing these arms, it will be 10,000.
Exactly. So it's a very violent environment compared to our own solar system at current state. Yep.
That's a key result, basically. But we're gonna go back to that. I'll let you finish this amazing table.
Yeah. So yeah, basically that's the last slides I want to share that summarize the numbers we find on the model. So we calculate the mass loss rate. So not only for the star, but also we calculate as a comparing case as the current sun. So you can see the mass loss rate of the Carbonaceti is 100 times more than the current sun. And also you can see the stellar wind is 2 times faster. And here we just see the figures that the dynamic pressure can be varying from 100 times to 1,000 times more than the dynamic pressure of Earth at current time. Yeah, and also we generate the synthesized X-ray emissions and the EUV emissions, and you can see that is a very big difference. Yeah.
So it means that if there is a planet around Kappa 1 Ceti, I need to find a way to simplify the name of this star. I have a hard time saying it. It implies that this planet is being kind of bombarded regularly by a very strong solar wind. If this planet has no magnetosphere to protect it, then this heavy bombardment will reach the surface, sterilizing the planet, right?
Exactly, yeah. And also what we know about our own Earth is that it has the magnetic field. So it's to shield us from the solar wind and the energetic particles. But so when you have a much stronger stellar wind in the Kappa 1 Ceti and also energetic particle from the stellar wind or the galaxy cosmic rays, these high energy particles can propagate easily into the atmosphere of the planet systems and broke the moleculars and generate this greenhouse gas. So that's tell you some clues about how the life is possible, or give you some ideas of how the process happens. So basically, it's can provide some important reference for this kind of studies.
All right. So we're gonna take some questions from the viewers, but I have some question myself while they are coming. So it's a very interesting result because you mentioned there is more bombardment, more radiation on the surface of Earth. If there was an Earth, there will be more around Kappa 1 Ceti. There will be those radiation. But it's interesting that this is the time at which life appears on Earth anyway, right?
Mm-hmm. Yeah.
So maybe the sun had the same kind of activity in the past, and maybe the life, in fact, appear because those radiations somehow help as well to produce mutations, destruction of those complex molecules that may have in it basically somehow life on our planet.
Mm-hmm.
We're not 100% sure. We cannot say that life did not appear. We cannot say that this heavy bombardment sterilize the surface of a planet. It may also help making this biology on the surface of the planet more active, and in it somehow this creation of life. But we're not there yet in our science. Let's go back to your study. So I have a question here. In your studies, first of all, can you clarify exactly what data point you have been getting? Is it a telescopes? Is it a space telescopes? Where those data are coming from?
We use a lot of observations in this study. So I will separate to the solar part and the stellar part. So for the solar part, we use the SDO observations from HMI, from AIA, and we also use the GOES that observing the soft X-ray emissions from the sun. And for the stellar part, we use the EOBE observations. So that is the satellite 20, 30 years ago, that observing the EOV band for the stars. And we also use the Hubble Space Telescope data. Okay. And for reconstruct the ZDI magnetogram, so actually we use the observations from two satellites, one in France and one in Chile. Yeah. So that these are spectral polynomial observations. Yeah.
It's interesting. You are showing the two telescopes that I use in my young. First time in my life I observed was the 2-meter telescope at the Pic du Midi, and then my PhD I did it at La Silla at the ISO 3.6-meter telescope. That's a coincidence. Oh. It's a very weird coincidence.
Yeah.
So I know those telescopes. Oh,
that's a surprise. Well. Yeah.
And my question was, I did not expect this answer on you. So I'm glad to see those telescopes again.
Right? Yeah, that's a suggestion. We need to collaborate, and the two fields are merging. I mean,
yes. So those are spectral polarimeter, meaning that they take the color with a very high resolution. I think we're talking about what for those 10,000, right? Something like that. And they also go ahead.
Sorry, you mean the waveband of the observation? I'm not. I think exactly sure. Yeah.
But then they do also the polarimetry. So that's allow you with the polarimetry, you get what? You get the geometry of the magnetic field, basically.
Basically, you can observe the Stokes parameters in the polarimetry, and then with that you can derive the vector magnetic field from these parameters. But for the star, because this is an integrated spectrum, is without spatial resolution, so you need like Zeeman Doppler imaging techniques to invert that information to actually 2D distribution of the field. Yeah.
Excellent.
And I think it is the band, probably the iron line, but I need to double check that.
That's okay. So we have a few more minutes to discuss this. I have a few questions here. So what is the cycle of the sun? And from your observations of this Kappa-1 Ceti, what is the solar cycle of this one?
So from just the two observations or the two period observations, we cannot decide exactly what is the stellar cycle of that star. You need more continuous observations and see how the field change. And so we don't know that in this study. Yeah.
Okay.
But what is sure is that it is much shorter than the current sun. So because you're observing the sun separated by 1 year, you probably cannot see that big change in the global topology of the field.
So what was the most surprising result of this paper, you think?
The most surprising, I think, yeah, is the magnetic change, the magnetic configuration change in just 1 year.
Yeah, okay.
So yeah, that's one surprising result. And yeah, for the model we build, for many of them, we know this is an active star and it's gonna generate stronger ring and more denser ring, more hotter corona. But before, we don't know a precise number of it. So I think the value of this study is that with the model, we can get more precise parameters that could be used to drive like the atmospheric models for the habitability studies. So.
Okay. And what's the next step? I saw that the title of this paper is 1 year in the life of young suns with an S at the end. So I'm assuming you have more targets to observe. What's the plan?
I think the first step we're gonna do, and actually we are doing now, is that we try to model the stellar CMEs, so stellar storms from this star. So we have the stellar ring already, so that we're trying to initiate coronal mass ejections based on this stellar ring. So we're gonna see another more violent event that could influence the planet systems. And the other things we do is that we also want to simulate the solar and stellar energetic particle event from that star, because from our sun studies, we know the coronal mass ejections can drive very strong shock, and these shocks can accelerate particles, and these high energetic particles can penetrate to the atmosphere of the Earth, and that result in the aurora light. So that we are trying to do simulate the stellar energetic particles also from Kappa-1 Ceti. And another plan we are trying to do is to apply this model that we developed in this study to other stars, that they do observe the exoplanet in that system. And so for that, we can get more critical information from the central stars of that system, and to provide to the scientists doing the habitability studies. So that's the two future plans.
So there's a two direction of your research. One is to focus to improve the modeling. Are you going to get more data, or you are going to use the data you have to do this to improve the modeling?
We will get more data for sure. Yeah,
that's the typical answer of any scientist. And then you are going to focus on some of the stars which are known to have planets, because I look, Kappa-1 Ceti doesn't have yet a detected planet, right? We have no idea.
Exactly. Yeah.
I wonder the
so that is a little bit disappointed.
Yes,
but there are a lot of exoplanet system as you discovered, Frank. So we're gonna look into other systems that they do have exoplanet detected. Yeah.
Excellent. I'm always amazed when I talk to heliophysicists. Because the research you do is always extremely complex in terms that you have so many different type of data that you need to collide to put together. And I do remember when this model came out, the Half-Then wave solar models. That's it seems to be kind of a revolution in your field because a lot of people have been using it, right?
Yes. Another thing we want to use this model is to do the space weather forecasting. So that is another big topic and can influence our life on Earth.
Yeah.
So yeah.
Yeah, I do like the fact that science works like that. Sometimes we are all writing our own tiny models on our side, and then one day someone say, you know what, we are going to combine our brains and create this masterpiece that we're gonna call the model so far, and we are going to improve it over time. But that will be basically what everybody in the community will be using. And this model is basically what this is. It's kind of a standard now in the field of heliophysics. And and I'm very glad we have you, man, at the SETI Institute to bring this perspective about the importance of stars and their activity, because we do know that for life, they are important, of course.
My great pleasure.
Anything else you want to add, man? Something that I did not mention in this about your research or your work?
I think that's it. But also, I want to mention that I think in the next decades, it's going to be a golden age for this solar stellar connection studies, and also connected to the exoplanet, because we have a JWST, and also we have several ongoing and coming up heliophysicist missions like Parker Solar Probe, like a solar orbiter. And at Lockheed, we're also doing another MIDEX mission called MUSE. So all these missions can bring us more insight about our own sun. And also the JWST, another mission I'm working also on this EUV emissions called ESCAPE. So all this can give us new data, new insights for both the solar and the stellar studies. And when we combine them together, yeah, we can build a very, we can head to the very big discoveries, I think.
Yeah, I would like to emphasize, if there is anybody here thinking about doing a thesis in astronomy, that we know now there is planets around every stars. We know there is different type of planets. There is one thing we don't really understand is the interaction between the stars and those planets. And as I say again, this is crucial to understand how you form life on a planet, okay? Because the star is the main source of energy for most planets in our galaxy. So the work you're doing is important, and I think with all these new missions and these new facilities that you mentioned, there will be more need for people to understand this kind of interaction. And JWST as well will play a major role to study those stellars, these young stars and the interaction with the planet. Well, thank you very much, Meng, for your time and for coming here.
Thank you, Frank.
Where are you located right now? I have no idea where. Are you in your office?
Yeah, I'm in my office. Yeah.
Okay.
Yeah.
Well, thank you, Meng. It was great talking to you, and I hope to have you back on the SETI Live to talk about more stars, young stars, toddler stars, and how they misbehave and they treat poorly their planets. Thank you.
Thank you, Frank.
So this was the SETI Live of this week, and I just remind you, this is a product of the outreach of the SETI Institute. The SETI Institute is a non-profit organization located in Mountain View, California. So if you like us, share our videos, join our social media, visit our website at seti.org. And you can also make a small donation to support these outreach efforts that we are doing for free for you. Any donation, anything from $1 to $2,000, $2 million. We will take all the money we can to make sure that we can understand how stars interact with their planets and support the research that Meng is doing here at the SETI Institute. So thank you very much to everybody, and I hope to see you next week or in 2 weeks. We talk about the wonder of the universe and planets, exoplanets, and life.